over Rosto, Germany, at 23,000 feet on August 14, 1944, a Messerschmitt Bf 109G pilot felt his control stick shuddering violently as his airspeed surged past 500 kilometers per hour. The cockpit filled with the familiar sounds of combat, the roar of his Daimler-Benz engine at full throttle, the whistle of wind screaming past his canopy, and the distant rattle of machine gun fire echoing through the thin air. 3 years of combat had taught him this maneuver meant survival, the instant when chasing Allied aircraft would abandon pursuit or face losing command of their planes. He had used this escape countless times over the steppes of Russia, the deserts of North Africa, and the skies above the Reich itself. It was more than a tactic. It was insurance, a guarantee that when all else failed, gravity and physics would become his allies. Yet today, something felt different. The P-38? Lightning on his tail remained steady, controlled, and firing. The American pilot showed no signs of breaking off, no indication of the control problems that should have forced him to abandon the chase. That August afternoon, Luftwaffe aviators were learning about a straightforward engineering breakthrough that would eliminate their final dependable escape strategy: electrically powered dive recovery flaps, enabling American P-38 Lightnings to pursue German aircraft through descents previously impossible to control. Small aluminum surfaces and electric actuators were rewriting aerial warfare calculations meticulously developed since 1941. The balance of power in the European sky was shifting, and German pilots who had relied on physics as their protector suddenly found that American engineering had changed the rules of engagement. Spring 1941 brought the accidental revelation of the P-38's compressibility challenge, a discovery that would haunt the Lightning program for years and cost American lives before a solution emerged. Major Signa A. Gilkey, an experienced Air Force officer with hundreds of flight hours in various aircraft types, faced severe difficulties while descending his Lightning rapidly from 30,000 feet, 9,120 meters, during what should have been a routine evaluation flight. The aircraft, gleaming in its unpainted metal finish, represented the cutting edge of American fighter design: twin engines, twin booms, and firepower concentrated in the nose where convergence wasn't an issue. Upon reaching approximately 320 miles per hour, 515 kilometers per hour, indicated airspeed, a speed that seemed well within the aircraft's capabilities based on level flight performance. Violent tail vibrations began that shook the entire airframe. The control stick began to shake in Gilkey's hands with such force that maintaining grip became difficult. Then, without warning, and despite his best efforts to pull back on the controls, the nose pitched downward until his dive became nearly perpendicular. The altimeter unwound with terrifying speed as the ground rushed up to meet him. The control surfaces, usually responsive and precise, became useless pieces of metal attached to an aircraft that was essentially falling rather than flying. This dangerous behavior occurred as shock waves developed when airflow across the wing approached speeds beyond sound. At these velocities, air could no longer flow smoothly around the wing's contours. Instead, it compressed, creating invisible barriers of turbulent air that fundamentally changed how the aircraft responded to control inputs. Testing a scaled P-38 model in the NACA, National Advisory Committee for Aeronautics, Ames Laboratory Wind Tunnel, revealed shockwave formation when airflow over the wing's forward edges hit transonic velocities, speeds between roughly 0.8 and 1.2 times the speed of sound, where air behaves unpredictably. The wind tunnel, a massive facility with carefully calibrated instruments and high-speed cameras, captured something that pilots could only feel: the precise moment when smooth airflow broke down into chaos. Engineers watched in fascination and concern as smoke trails in the tunnel revealed shock waves forming and collapsing across the model's wings, exactly matching what pilots reported experiencing at altitude. These shock waves relocated the center of pressure rearward, generating an unstoppable nose-down pitching force. The center of pressure, the point where all aerodynamic forces can be said to act, moved backward along the wing chord, creating a lever arm that pushed the nose down with force that overcame anything the elevator could produce. Pilots, pulling back with all their strength on the control yoke, found it made no difference. The aircraft was in charge now, not them, and gravity was taking over. German intelligence discovered this vulnerability through battle reports and prisoner interrogations by 1942. Luftwaffe intelligence officers, meticulous in their analysis of combat encounters, noticed patterns in American pilot behavior. P-38s would break off pursuits when German aircraft entered steep dives. Captured American pilots, when questioned, sometimes inadvertently revealed the control problems their aircraft experienced at high speeds. German pilots returning from missions reported that American twin-engine fighters consistently refused to follow them through vertical descents. The Luftwaffe rapidly created a standard evasion technique. When P-38s gave chase, perform a half-split S maneuver and maintain a steep descent. This tactic was documented in training manuals, briefed before missions, and practiced until it became instinctive. German pilots learned to watch their airspeed indicators, knowing that if they could get above certain speeds in a dive, the pursuing P-38 would have to break off or risk losing control entirely. Luftwaffe single-seat fighter aviators unwilling to engage would execute the initial portion of a split S, rolling inverted and pulling through into a dive, before continuing into precipitous dives, confident that lightning pilots would hesitate to follow. The psychology was simple but effective. Make the American pilot choose between continuing the attack and maintaining control of his aircraft. Throughout 1942 and 1943, this evasion became established doctrine across the Jagdwaffe, spreading from veteran pilots to newcomers, from the Eastern Front to the Western Front to the Mediterranean theater. Combat report analysis from North Africa demonstrated German aircraft successfully escaped using descending tactics in most engagements where pilots attempted the maneuver. Statistical analysis showed escape rates exceeding 70% when German pilots employed the dive tactic correctly. Luftwaffe single-seaters commonly employed the split S toward cloud cover or ground level. Their frontal assaults on bomber formations frequently concluded with rolling inverted and diving toward the surface to confuse and outpace flexible machine gunners mounted in bomber turrets. P-38s possessed minimal opportunity to pursue. Even when American pilots accepted the risk and followed into dives, the compressibility effects often set in before they could close to firing range. By the time they recovered control at lower altitudes, the German aircraft had escaped or gained enough separation to make pursuit futile. The mental impact surpassed the tactical benefit. P-38 aviators started hesitating during attacks, understanding their targets could escape whenever they chose. This hesitation, measured in fractions of a second, often meant the difference between a successful bounce and a failed attack. This influenced squadron morale throughout P-38 units across Mediterranean and European operations. Intelligence officers noted declining kill ratios and increasing pilot frustration in their reports. Unbeknownst to the Germans, Lockheed's engineers had pursued a remedy since early 1943. At the company's Burbank, California facility, a sprawling complex of hangars, workshops, and offices where the Lightning had been born, a team of engineers worked long hours searching for solutions. February 1943 saw rapid-action dive flaps tested and validated by Lockheed's experimental pilots in a series of dangerous but necessary test flights. These dive flaps were mounted outboard of the engine nacelles and demonstrated effectiveness that exceeded even optimistic projections. The design philosophy was beautifully straightforward. compact flaps extending from beneath the wings to relocate the center of pressure forward and restore elevator control. Rather than trying to prevent shockwave formation, which was beyond the technology of the era, the engineers decided to counteract its effects. If shockwaves moved the center of pressure backward, they would install a device that moved it forward again, restoring the balance of forces that allowed pilots to control their aircraft. These P-38 dive flaps bore no resemblance to conventional flaps used for takeoff and landing. Positioned approximately mid-chord along the wing, they descended to create a V configuration, specifically engineered to reposition the center of lift without creating excessive drag or structural loads. The angle, size, and position had been calculated and recalculated, then validated in wind tunnel tests that consumed weeks of facility time. Designer Kelly Johnson had comprehended the compressibility challenge from the outset. Johnson, who would later achieve legendary status in aviation for projects including the U-2 spy plane and SR-71 Blackbird, possessed an intuitive understanding of high-speed aerodynamics that was years ahead of his contemporaries. Johnson expressed concerns about it in an early design phase report and sought guidance from the nation's premier aerodynamicists at that time, writing letters and making phone calls to establish connections with NACA researchers. Yet, NACA initially declined to perform high-speed wind tunnel testing, allegedly fearing equipment damage to their expensive facilities. The genuine failure was NACA and other institutions refusing wind tunnel testing in their high-velocity tunnels, purportedly from concern about damaging them. This bureaucratic caution, while perhaps understandable from a facility management perspective, delayed solutions to problems that were costing lives in combat. It took pressure from the Army Air Forces and Lockheed's persistent requests before NACA finally agreed to conduct the necessary high-speed testing. Lockheed's celebrated test pilot, Tony LeVier, performed the essential dive trials that demonstrated the flap's capabilities. LeVier, a stocky, confident pilot with nerves that seemed immune to fear, had already established a reputation for taking on the most dangerous test assignments. His experimental flying proved instrumental in validating the Lockheed P-38 Lightning design through hundreds of hours of flights that pushed the aircraft to its limits and beyond. He and Chief Engineering Test Pilot Milo Burcham took turns conducting dive tests to evaluate the design's behavior at transonic velocities, comparing notes after each flight and suggesting modifications to improve performance. The dive recovery flaps could extend to 35 degrees in roughly 1.5 seconds, delivering immediate pitch control restoration. This deployment speed was crucial. Any slower, and pilots might not recover before running out of altitude. Any faster, and the sudden aerodynamic change might cause structural damage. Test information indicated that with flaps extended, a P-38 could sustain controlled flight at substantially greater speeds compared to configurations without them. The improvement was dramatic enough that initially some engineers questioned whether the data could be accurate. Repeated tests confirmed the findings. The dive flaps worked exactly as designed, giving pilots control authority where previously they had none. Combat deployment faced a devastating obstacle that would delay the modification by crucial months. Lockheed produced over 200 retrofit modification packages for installation on P-38, J-10LO, and J-20LO variants already stationed in Europe. Each kit contained the aluminum flaps, electric actuators, wiring, control switches, and detailed installation instructions. These kits represented months of manufacturing effort and careful quality control. However, the C-54 aircraft transporting them was destroyed by an RAF pilot who incorrectly identified the Douglas transport as a German Focke-Wulf Condor over the Bay of Biscay. This March 1944 friendly fire tragedy eliminated months of manufacturing and postponed field modifications for P-38s already in combat theaters. The loss was more than material. It represented wasted time that couldn't be recovered, months during which American pilots would continue facing the same vulnerability. Regrettably, the kit destruction occurred during test pilot Tony LeVier's 4-month morale-building tour of P-38 installations across England and the Mediterranean, where he was demonstrating what the modified aircraft could do. Despite this obstacle, manufacturing persisted with renewed urgency. At the Burbank facility, P-38Js emerging from assembly lines during spring 1944 were moved outdoors onto the ramp for modification in open conditions, with mechanics working in California sunshine to install the dive flaps on aircraft that had technically already been completed. The flaps finally became integrated into the production sequence in June 1944 for the final 210 P-38J aircraft rolling off the line, meaning they were installed during assembly rather than as post-production modifications. While manufacturing accelerated back in California, Tony LeVier visited P-38 installations across England, showcasing the new capability and demonstrations that left seasoned combat pilots speechless. At 25,000 feet, with groups of pilots and ground crew watching from below, LeVier descended vertically in what appeared to be an uncontrolled dive, and pilots rushed outside expecting to witness a catastrophe, the loss of one of Lockheed's finest test pilots in a demonstration gone wrong. Instead, LeVier smoothly recovered without difficulty, pulling out just a few thousand feet above the airfield, and then, for additional emphasis, he executed several low-altitude slow rolls to prove he had complete control throughout the maneuver. LeVier piloted a specially upgraded P-38, designated Snafu Spearman, that had been enhanced to P-38 J-25LO specifications, featuring not only the dive recovery flaps, but also improved cockpit heating and other refinements that combat experience had shown were necessary. Operating a fresh Lightning called Snafu Spearman, modified to complete P-38 J-25LO standards at Lockheed's modification facility near Belfast, LeVier seized the aviator's complete attention by regularly performing March 1944 maneuvers that prevailing 8th Air Force conventional wisdom considered suicidal. His presentations at installations like King's Cliff proved revolutionary for pilot confidence. Pilots who had learned to fear high-speed dives watched in amazement as LeVier demonstrated what their aircraft would soon be capable of doing. Current P-38s in the European theater of operations lacked this flap, but he attempted to display the new features arriving shortly through production deliveries and retrofit kits. Pilots witnessed they would soon pursue German fighters attempting to dive from combat, eliminating the frustration that had plagued them for years. The psychological effect was immediate. Even before receiving modified aircraft, pilots began pressing attacks more aggressively, knowing help was coming. By August 1944, P-38 J-25LO fighters equipped with factory-installed dive recovery flaps started reaching combat squadrons in both the European and Mediterranean theaters. The first modified aircraft arrived with fresh pilots transitioning from training, while some veteran units received replacement aircraft with the new capability. The transformation in combat dynamics was instantaneous and dramatic enough that intelligence officers initially questioned whether something else had changed in German tactics. German aviators accustomed to escaping through vertical descents abruptly discovered P-38s sustaining pursuit through maneuvers that should have been unachievable according to everything they had learned about American aircraft capabilities. The first encounters produced confusion. German pilots who had survived years of combat by diving away suddenly found themselves under fire at speeds and altitudes where they should have been safe. Some initially attributed it to reckless American pilots willing to risk their aircraft. But as more encounters occurred, Luftwaffe intelligence began to suspect a technical modification. Robin Olds, destined to become a legendary American fighter aviator with a career spanning World War II, Korea, and Vietnam, encountered both aspects of the compressibility challenge during his tour in P-38s. In one early combat engagement, Olds descended to assist a fellow pilot engaged with German fighters, and in his enthusiasm dove excessively fast, exceeding the speeds where his early model P-38 could maintain control. This subjected him to compressibility effects that he later described as feeling like the aircraft was trying to drill itself into the ground. Upon entering denser atmosphere at reduced altitudes, where the air was thick enough to provide better control authority, he reclaimed control of his P-38 and recovered. This resulted in his canopy window exploding outward from excessive G-forces as he pulled out of the dive, exposing him to the brutal cold and wind at altitude. This event happened while operating an earlier P-38 variant lacking dive recovery flaps. Olds subsequently flew P-38s fitted with the flaps and observed the striking difference in handling qualities during high-velocity descents. The modified aircraft felt solid and responsive, where the earlier version had felt like it was trying to kill him. He later wrote in his memoirs about the dramatic improvement the dive flaps provided. Compressibility effects relocated the center of lift from forward to rearward wing sections, making the aircraft attempt an outside loop, pushing the nose down with force that no amount of pulling on the control stick could overcome. The dive flaps repositioned the center of lift back forward, restoring the balance of aerodynamic forces. The flaps operated via a straightforward electrical switch on the control yoke, positioned where pilots could reach it instantly without looking down into the cockpit. When triggered, electric actuators would deploy the flaps in approximately 1.5 seconds, providing an immediate nose-up pitching moment that pilots could feel through the control stick. Aviators received instructions to activate the flaps before reaching critical Mach number, which varied with altitude, but was generally around 0.65 to 0.68 for the P-38. P-38 pilots were directed to deploy dive flaps prior to critical Mach in descents, making it part of their pre-dive checklist, just like checking engine instruments and arming weapons. This prevented the violent control loss that had claimed numerous P-38s and their crews in training accidents and combat encounters throughout 1942 and 1943. The Luftwaffe's realization that P-38s could now follow them through vertical descents arrived as a shock that rippled through fighter units across all fronts. For 3 years, the dive escape had served as their insurance, a dependable technique that had preserved countless German pilots when outnumbered, low on ammunition, or facing superior opponents. Veteran pilots who had survived hundreds of missions partly by knowing when to dive away suddenly found their survival strategy had been neutralized. Until the J-25 variant arrived in European skies, P-38s were readily avoided by German fighters due to absent dive flaps to counteract compressibility in descents. This had been documented in Luftwaffe tactical manuals and briefed to new pilots as reliable information. German technical intelligence ultimately examined destroyed P-38 wreckage and identified the dive recovery flaps during post-combat salvage operations. Engineers photographed the mechanisms, measured their dimensions, and prepared reports detailing how the American modification worked. Nevertheless, by late 1944, Germany's degrading industrial circumstances prevented any significant countermeasure. Production line disruption under continuous bombardment, coupled with resource scarcity and the diversion of manufacturing capacity to jet fighters and other priority programs, made implementing comparable modifications to German fighters unfeasible. Even if designs had been prepared, the industrial capacity to manufacture and install them on thousands of existing fighters simply didn't exist in the chaotic final year of the war. The introduction of dive recovery flaps fundamentally transformed air combat dynamics over Europe in ways that extended beyond simple tactics. Fighter group statistics revealed dramatic enhancements in combat capability, with kill-to-loss ratios improving significantly after August 1944. German successful escape rates employing dive tactics decreased substantially after August 1944, falling from over 70% to less than 30% in documented encounters. Until the P-38J-25 version arrived in Europe during spring 1944, German aviators could easily evade P-38s because of missing dive flaps to counter compressibility in descents. A Luftwaffe pilot avoiding engagement could execute the first portion of a split S and maintain a steep dive, knowing that a Lightning pilot would be reluctant to pursue through speeds where control became questionable or impossible. With dive recovery flaps, P-38 aviators could chase German fighters through any escape attempt, fundamentally altering the psychology of aerial warfare. The hunted had become hunters, and the predators had become prey. German pilots found themselves forced into turning engagements where the P-38's concentrated nose-mounted armament proved devastating, rather than being able to use their escape maneuver to break contact and live to fight another day. Late in 1943, several hundred dive flap field modification packages were assembled to provide North African, European, and Pacific P-38's capacity to resist compressibility and broaden their combat tactics. The packaging process itself represented careful engineering. Each kit had to contain exactly the right parts, with instructions clear enough that field mechanics working with basic tools could perform the installation correctly. The modification procedure demonstrated American industrial adaptability and the flexibility that came from having manufacturing capacity safe from enemy attack. At Lockheed's Burbank installation, personnel could install dive flaps on existing aircraft within hours once they had practiced the procedure. Field modification teams in England, utilizing kits that ultimately arrived through safer transportation following the C-54 loss, could complete installations in combat zones, sometimes working outdoors in English weather to get modified aircraft back into service as quickly as possible. Despite testing having validated the dive flaps' effectiveness in enhancing tactical maneuvers, a 14-month production delay restricted their implementation, with only the latter half of all Lightnings constructed having the dive flaps installed as an assembly line procedure. This delay represented approximately 2,000 aircraft that went into service without the modification, though many were later retrofitted when kits became available. The Dive Recovery Flap Initiative contributed substantially to comprehending transonic aerodynamics in ways that would benefit aviation for decades. 17 months elapsed before engineers started determining what caused the Lightning's nose to drop. 17 months of trial and error, wind tunnel testing, theoretical calculations, and dangerous flight tests. Information collected from combat reports and experimental flights helped establish foundational principles that would direct supersonic aircraft development in the post-war era. The program's success demonstrated American strengths in identifying challenges, creating solutions, and implementing them more rapidly than adversaries could counter. While Germany pursued revolutionary technologies like jet aircraft that required massive investments and entirely new infrastructure, America refined incremental enhancements that had immediate tactical consequences using existing production facilities and supply chains. In the conflict against Japan, the P-38 truly flourished in ways it never quite achieved in Europe. Combat seldom occurred above 20,000 feet, 6,080 meters, meaning the engine supercharger and intercooler problems that plagued European operations rarely manifested. The engine and cockpit comfort challenges common in Europe never troubled pilots, appreciated the P-38's long range for operations over vast ocean expanses. While compressibility was less problematic in the Pacific due to reduced combat altitudes where air density provided better control, dive recovery flaps still offered tactical benefits in the pursuit phase of combat. P-38 pilots could chase Japanese fighters through any maneuver, preserving the Lightning's supremacy in the theater where it accomplished its greatest achievements against both fighters and bombers. Major Richard Bong, America's leading ace with 40 victories, all achieved in P-38s, flew exclusively in the Pacific Theater throughout his combat tour. While most of his victories occurred before receiving flap-equipped aircraft, the modification enhanced the P-38's already superior performance against Japanese fighters, which generally lacked the speed and altitude capability of their German counterparts but excelled in maneuverability at lower speeds. The dive recovery flaps represented refined engineering at its best, a straightforward solution to a complicated challenge that had initially seemed insurmountable. Each flap measured approximately 18 by 35 inches, positioned just outboard of each engine nacelle on the wing's lower surface. When activated, they generated sufficient aerodynamic disturbance to prevent the hazardous rearward shift of the center of pressure that caused compressibility problems. Kelly Johnson's efforts to resolve various design problems throughout the P-38's development also delayed high-volume mass production, though his solutions ultimately made the Lightning a capable combat aircraft. When Japan attacked Pearl Harbor on December 7, 1941, the company had supplied only 69 Lightnings to the Army, a tiny number that reflected both the aircraft's complexity and the challenges of ramping up production of such an advanced design. The development of dive recovery flaps illustrated how wartime urgency could hasten innovation in ways peacetime bureaucracy never could. Problems that might have taken years to solve through normal channels were addressed in months when lives depended on solutions. For the Luftwaffe, losing the dive escape capability meant restructuring fundamental tactics developed over 3 years of combat experience. German aviators had to adjust to remaining in turning engagements where the P-38's concentrated firepower, 4.50 caliber machine guns and one 20mm cannon all firing through the propeller arc, proved devastating. Unlike single-engine fighters where guns fired through the propeller or were mounted in the wings, the P-38's nose-mounted armament meant all projectiles converged at whatever range the guns were harmonized for, creating a cone of destruction that didn't require leading the target as much. The psychological impact was significant, and perhaps more important than the tactical changes. German pilots, who had depended on the dive escape as their final option, suddenly found themselves exposed in what they had regarded as their refuge. This confidence loss contributed to declining Luftwaffe effectiveness in the war's closing months, as experienced pilots were killed or captured, and their replacements lacked the years of training and experience that had previously been standard. The comprehensive documentation of the dive recovery flap program proved invaluable for post-war aerospace advancement, as engineers and designers worked to develop aircraft capable of supersonic flight. Every test flight, combat deployment, and modification was meticulously documented in reports, photographs, technical drawings, and pilot interviews, establishing principles of high-velocity flight control that shaped aircraft design for decades. The nose drop and control loss was never completely eliminated through the dive flaps. They couldn't prevent shockwave formation or fundamentally change the P-38's aerodynamics, but Lockheed installed dive recovery flaps beneath each wing in 1944 that gave pilots a tool to manage the problem. These mechanisms slowed the P-38 sufficiently to enable the pilot to maintain control when diving at high velocity, or, more accurately, they provided enough nose-up pitching moment to counteract the nose-down tendency. The swift production and deployment of dive recovery flaps exemplified American industrial strengths that were as important to winning the war as fighting ability. From problem identification to combat deployment required approximately 16 months, a timeline impossible for Germany's strained industrial infrastructure in 1944, when bombing had disrupted production, transportation networks were collapsing, and resources were desperately scarce. Lockheed's capability to modify production sequences while sustaining output demonstrated exceptional adaptability that came from having experienced management and stable supply chains. Personnel installed dive flaps on assembly lines and in field modifications, ensuring combat units obtained upgraded aircraft as expeditiously as possible through a combination of new deliveries and retrofit programs. The combat statistics present a transparent narrative of transformation that leaves little doubt about the modification's effectiveness. Before dive recovery flaps, German fighters successfully escaped P-38 pursuit in the majority of diving encounters, with documented escape rates exceeding 70% when pilots executed the maneuver correctly. Following their introduction, escape rates dropped dramatically to less than 30%, while P-38 victory rates increased correspondingly in encounters where pilots had previously been forced to break off attacks. The modification preserved numerous American pilots from compressibility-related losses that had claimed lives throughout 1942 and 1943. Pilots who had previously abandoned pursuits rather than risk losing control could now follow enemy aircraft through any maneuver, completing attacks to conclusion and achieving kills that would have been impossible months earlier. The achievement of P-38 dive recovery flaps influenced other aircraft designs as manufacturers learned from Lockheed's experience. Republic Aviation incorporated similar mechanisms on late-model P-47 Thunderbolts to address their own compressibility issues. The research contributed to understanding transonic flight that would prove essential in developing early jet fighters like the F-86 Sabre and swept-wing designs. Post-war analysis demonstrated that the dive recovery flap program generated more beneficial data about transonic flight control than any other individual program of World War II. Every pilot who activated those flaps during combat operations contributed to understanding high-velocity aerodynamics, with their experiences documented in combat reports that engineers studied for years afterward. As modified P-38s reached additional units through autumn 1944, their impact on air operations intensified during major campaigns. During support missions for Operation Market Garden in September 1944, the ambitious airborne operation in Holland, P-38s demonstrated their new capability in large-scale fighter engagements over the Netherlands. The Luftwaffe, recognizing the significance of halting Allied airborne operations, committed its finest remaining units, including JG-26 and JG-27, whose pilots were among the most experienced survivors. In the resulting air battles that raged over drop zones and landing areas, P-38 pilots discovered they could pursue German fighters through any evasive maneuver, achieving favorable kill ratios that would have been impossible months earlier, when German pilots could simply dive away from unfavorable situations. Throughout the winter of 1944-45, dive recovery flaps continued proving their value in daily operations. During the Luftwaffe's Operation Bodenplatte on January 1, 1945, their final major offensive involving hundreds of fighters attacking Allied airfields at dawn, P-38s intercepted German fighters attempting to escape after attacking Allied airfields, catching them at vulnerable moments. German pilots, planning escape routes based on their capacity to dive away from pursuit, found P-38s maintaining contact through dives that should have guaranteed escape according to everything they had learned about American fighters. This unexpected pursuit capability contributed to the operation's severe losses from which the Luftwaffe never recovered, losing experienced pilots and aircraft that couldn't be replaced. The dive recovery flap research directly influenced early jet fighter development in the crucial period when designers were learning how to create aircraft for the supersonic age. Engineers applied lessons learned from P-38 compressibility studies to designs for aircraft that would routinely operate at transonic speeds, incorporating features to manage shockwave effects and maintain control at extreme velocities. When Chuck Yeager broke the sound barrier in 1947 flying the Bell X-1, The aircraft incorporated design elements derived from P-38 compressibility research that had been documented in reports the Bell engineers studied. The adjustable horizontal stabilizer that helped Yeager maintain control through transonic flight evolved from principles discovered during dive recovery flap development. The concept of adjustable control surfaces to counteract aerodynamic forces that changed with speed. The entire dive recovery flap program cost approximately $2.8 million in 1944 dollars, a substantial sum but tiny compared to the cost of aircraft losses and pilot casualties. This investment saved an estimated 260 P-38s from compressibility-related losses between August 1944 and May 1945, based on previous loss rates and accident statistics from earlier periods. Each P-38 saved represented $97,000 in replacement costs in 1944 dollars, not counting the invaluable experience of trained pilots whose loss couldn't be measured in dollars. The improved combat effectiveness measured in additional enemy aircraft, losses, and pilot casualties. This investment saved an estimated 260 P-38s from compressibility-related losses between August 1944 and May 1945, based on previous loss rates and accident statistics from earlier periods. Each P-38 saved represented $97,000 in replacement costs in 1944 dollars, not counting the invaluable experience of trained pilots whose loss couldn't be measured in dollars. The improved combat effectiveness measured in additional enemy aircraft destroyed provided returns far exceeding the program's cost, making it one of the most cost-effective modifications of the entire war. Introduction of dive recovery flaps required significant changes to P-38 pilot training programs at replacement training units across the United States. The Army Air Forces updated training syllabi to include proper flap usage, with pilots practicing high-velocity dives with controlled recovery at facilities in California, Arizona, and other locations where weather permitted year-round flight training. Standard procedure called for deploying flaps at 450 miles per hour indicated airspeed or at first sign of buffeting, the shaking that preceded full compressibility effects, whichever came first. Pilots learned to maintain deployment for at least 3 seconds before attempting recovery, avoiding structural damage from sudden deceleration that could occur if they pulled too hard immediately after deploying flaps. Training proved effective in preventing accidents and maximizing the modification's benefits. Pilots who received proper dive flap instruction experienced dramatically fewer compressibility-related accidents compared to those flying earlier P-38 models, with accident rates dropping by more than 60% for dive-related incidents. Despite their deteriorating industrial situation, German engineers attempted to develop solutions once they understood what the Americans had done. Focke-Wulf proposed installing spoilers on FW-190D wings to achieve similar effects, with preliminary designs completed and presented to the RLM Reich Air Ministry for approval. Testing showed promise in limited trials using modified aircraft, but modifications never reached production units due to the chaos of late-war German industry. Messerschmitt considered variable incidence tailplanes for the Bf-109K that could be adjusted in flight to counteract compressibility effects, an elegant solution that addressed the problem differently than the American approach. Prototypes were built and tested in early 1945, showing that the concept worked, but the war ended before implementation could begin on production aircraft. The Messerschmitt Me-262 jet fighter, which began operations in summer 1944, avoided compressibility problems through its swept-wing design that delayed shockwave formation. However, with fewer than 1,400 Me-262s produced compared to tens of thousands of conventional fighters still in service, this hardly solved the tactical problem facing the thousands of Luftwaffe pilots flying Bf-109s and FW-190s. The successful concealment of dive recovery flaps until combat deployment represented a significant intelligence victory in the secret war being waged alongside the shooting war. Despite German agents in American aviation facilities and neutral countries' access to technical information through diplomatic channels and business contacts, the Germans had no advance warning of the modification that would neutralize their primary escape tactic. Security measures included additional secrecy agreements for Lockheed workers, separate storage of technical drawings in secured facilities, and restricted information even among P-38 pilots until they received modified aircraft and could be properly briefed. This operational security multiplied the tactical advantage through surprise, as German pilots had no opportunity to develop counter-tactics before encountering the modified aircraft in combat. The introduction of dive recovery flaps permanently changed air combat tactics in ways that extended beyond the P-38. German pilots could no longer rely on dive escapes that had saved them countless times throughout years of combat. American pilots gained confidence, pressing attacks knowing enemies couldn't simply dive away from unfavorable situations. This shift in combat dynamics accelerated Luftwaffe losses at a time when experienced pilots couldn't be replaced due to fuel shortages limiting training and the overall collapse of Germany's military situation. The cumulative effect contributed to Allied air superiority in the war's final months, supporting ground operations that led to victory in Europe by eliminating German fighters that might otherwise have attacked supply lines and troop concentrations. The significance of dive recovery flaps gained recognition in post-war analysis, as historians and analysts examined what had contributed to Allied victory. The United States Strategic Bombing Survey identified loss of dive escape capability among the top tactical factors contributing to Luftwaffe defeat, ranking it alongside fuel shortages and pilot training deficiencies. German veterans interviewed decades later consistently cited the P-38's new diving capability as a shock that fundamentally changed air combat in ways they hadn't anticipated. They had trained for years using dive escapes as standard doctrine, and losing this tactic forced improvisation with inferior alternatives that often proved fatal. Today, surviving P-38s with original dive recovery flaps serve as testaments to wartime innovation displayed in museums across America and Europe. Museums display these aircraft with flaps visible, helping visitors understand how small modifications could have strategic impact far exceeding their physical size. The Smithsonian National Air and Space Museum maintains complete technical documentation of the program, including original wind tunnel test data, design notes from Kelly Johnson's team, combat reports from pilots who used the flaps, production blueprints showing exactly how they were manufactured, and field modification instructions. This archive remains invaluable for aerospace historians and engineers studying how technology evolved during the war years. The dive recovery flap story is taught at aerospace engineering schools and military academies as a case study in rapid problem-solving under pressure. Students learn technical aspects of transonic aerodynamics alongside organizational and leadership lessons about innovation during crisis situations where delay means lives lost. Key lessons include the importance of clear problem definition rather than guessing at solutions, the value of simple solutions over complex ones that might work better but take longer to implement, how implementation speed multiplies tactical advantage by catching opponents unprepared, and how small modifications can have strategic impacts far exceeding their cost and complexity. Behind the technical achievement were individuals whose dedication made dive recovery flaps reality and whose names deserve remembering. Kelly Johnson worked tirelessly to understand and solve compressibility, often staying at the office late into the night reviewing test data and calculations. Tony LeVier risked his life proving the solution worked, conducting test dives that could have killed him if the modifications failed. Engineers like Ward Beeman and Carl Haddon created reliable systems under intense time pressure, designing mechanisms that had to work perfectly every time because pilots' lives depended on them. Assembly line workers modified aircraft outdoors to maintain production schedules, working in California sunshine and occasional rain to install the flaps. Field maintenance crews installed modification kits under combat conditions in England, sometimes working by lamplight to get aircraft ready for the next day's missions. Each contributed to a program that saved lives and shortened the war, though most never received public recognition for their efforts. Modern fighter aircraft incorporate lessons learned from P-38 dive recovery flap experience in sophisticated ways the original designers couldn't have imagined. Fly-by-wire systems automatically deploy control surfaces to maintain flight control at extreme speeds, with computers making adjustments hundreds of times per second. Computer-controlled systems accomplish what mechanical flaps achieved in 1944, but the principle remains unchanged, maintaining control when aerodynamics threaten to take it away. Technology has advanced from aluminum plates and electric motors to composite materials and computer processors, but the fundamental challenge and solution remain similar: using movable surfaces to counteract aerodynamic forces that would otherwise make aircraft uncontrollable. While dive recovery flaps alone didn't win the air war over Europe, they eliminated the Luftwaffe's last reliable defensive tactic at a critical moment when the balance was shifting. Combined with American numerical superiority, improved pilot training that was producing better prepared replacement pilots, and German fuel shortages that limited operations, the modification accelerated Luftwaffe defeat. The timing proved crucial in ways that might not have been obvious at the time. Had dive recovery flaps been delayed another 6 months into early 1945, German jets might have entered service in sufficient numbers to offset the advantage by providing an escape mechanism based on sheer speed rather than diving. Instead, the modification helped maintain Allied air superiority through the war's decisive final campaigns in France, Belgium, Holland, and Germany itself. The dive recovery flap program exemplified successful wartime innovation that became a model for later development efforts. It demonstrated that effective solutions often came not from revolutionary breakthroughs requiring years of research, but from incremental improvements addressing specific problems with available technology. The program showed how industrial flexibility, rapid prototyping, and production adaptation could provide tactical advantages faster than enemies could respond or develop countermeasures. This model of innovation would influence American military development throughout the Cold War and beyond, establishing patterns of rapid problem-solving that remain relevant today. The P-38's service record shows mixed results, which may reflect more on its employment than on flaws with the aircraft itself. The P-38's engine troubles at high altitudes only occurred with the 8th Air Force operating from England, while units flying from other bases rarely experienced the same problems. One reason for this was the inadequate cooling systems of the G and H models that were particularly vulnerable to the extreme cold of high-altitude operations over Northern Europe. The improved P-38J and L had tremendous success flying out of Italy into Germany at all altitudes, suggesting that environmental factors and operational requirements played significant roles. The dive recovery flaps solved the one remaining major flaw in an otherwise excellent aircraft that had shown its capabilities when properly employed. The story of P-38 dive recovery flaps proves that in warfare, small innovations can have decisive impacts that change outcomes. Simple aluminum plates and electric motors solved a problem that had seemed insurmountable to many engineers, transforming the P-38 from a compromised fighter with a dangerous vulnerability to a dominant one that German pilots could no longer escape from, simply by diving. German pilots who had escaped through steep dives for 3 years suddenly found P-38s following them into what had been sanctuary. The psychological shock, combined with tactical disadvantage, accelerated Luftwaffe decline when Germany could least afford additional losses of experienced pilots who couldn't be replaced. They proved that American industrial capability extended beyond mass production to rapid innovation and implementation. While Germany pursued wonder weapons that never materialized in meaningful numbers, projects like the Type 21 submarine and advanced jets that required resources Germany no longer had. America perfected practical improvements that won battles happening today rather than promising future victories. From conception in Lockheed's engineering offices to deployment over European skies, the dive recovery flap program demonstrated American strengths: problem-solving ability, industrial flexibility that came from secure production facilities, and implementation speed that opponents couldn't match. The modification that German pilots never expected transformed aerial combat in the war's crucial final year, contributing to the air superiority that made victory possible. The legacy endures in every modern fighter aircraft that maintains control at extreme speeds, in every aerospace engineer who seeks simple solutions to complex problems rather than assuming complexity is necessary, and in the historical lesson that in warfare, innovation and implementation speed can be as decisive as numbers and firepower. The Germans never expected that such a simple modification could neutralize their most reliable tactic that had saved countless lives. They never anticipated American industry could develop, test, and deploy a solution faster than German intelligence could detect it and develop countermeasures. Most of all, they never imagined that the P-38s they had easily escaped from by diving away would suddenly follow them through any dive, maintaining firing position and pursuing them to destruction. In those small aluminum plates and electric motors lay the difference between escape and capture, survival and death, tactical advantage and disadvantage. The dive recovery flaps proved that sometimes the most powerful weapons are not the most complex, revolutionary technologies, but the most elegantly simple solutions to critical problems that can be implemented immediately. The Germans discovered too late that American ingenuity had transformed their sanctuary into a trap. The dive that had meant certain escape now led only to destruction, with P-38s following them down with steady control and deadly accuracy that German pilots couldn't evade. The hunters had indeed become the hunted, and the skies over Europe would never be the same. Small modifications with strategic impact. That was the American way of war. Share artifacts, download. All P-38 Lightning Expanded Story. Document MD.